In this video, we're going to talk about polynomial and rational inequalities and how to solve them both algebraically and graphically. So in our first example, our polynomial that we're given is x plus 3 times the quantity of x minus 1 squared is less than 0. So we're going to be asked to solve this graphically. We could solve this algebraically as well, but let's just look at the visual. So what I'm asked to do here is to graphically find all of the x values that will satisfy this inequality here. Notice I say solutions because there's going to be more than one x that could possibly create this less than 0 thing here. Hence the inequality notion. So I'm looking at this graph, and when I think less than 0, this whole thing is telling me like its y is less than 0. So it's where the function hits on the negative y-axis. So that's all of the numbers here down. Now I notice that really that only happens here. So if it was less than or equal to 0, it would include this point, but it's not because it doesn't have that equals to part. And it also won't include this point. But I notice that it is at negative 3, or x equals negative 3. So I can express that in two different ways. I can use set builder to say that x is going to be an element of all real numbers, and x has to be less than negative 3. Or we can write it in interval notation as negative infinity comma negative 3 with a parentheses around both, because infinity will not include, so it's going to have a parentheses instead of a bracket. And then here, it's going to be parentheses because it's not going to include that point because of our original inequality that was given to us. Now let's take a look at an example of a rational function. So I'm going to have x minus 1 all over x squared minus 4 is greater than or equal to 0. And I'm going to be asked to solve that graphically. So as I'm looking at this, just like in the last problem, I notice that this is like saying y is greater than or equal to 0, which means that I care about the positive y's, including 0, because it has that inequality symbol. So my next step is to take a look at what parts of the function actually exist at y is greater than or equal to 0. So I notice that if I start at x equals 1 right here, and I move to the left, I notice that that part of the function is above the x-axis, which satisfies part of my inequality here. Now, I notice also that it tapers off right at about x equals negative 2. There's going to be an asymptote running up x equals negative 2. Same thing with x equals positive 2 right here, which is where this other part of the function begins. And I also have to notice that as this third piece of the function here approaches positive infinity on the x-axis, it's going to taper off and approach the x-axis, but it will never touch it. So it will forever go on in this direction and be positive along the y-axis for our x values. So the way that we express the solution here is that x is an element of all real numbers, and its negative 2 is less than x, which is less than or equal to 1. So it's not negative 2 is less than or equal to x because it will never touch that negative 2 over here, but it will touch x equals 1 over here, and also including this inequality. So it can touch the x-axis according to this. Or our values here, where we'll start at 2, but we won't be able to touch it because there's that asymptote right there. Same thing with the negative 2. So it's going to be or x is greater than 2. And if I want to write it in interval notation, it would look like this, with a parenthesis on negative 2, a bracket on 1, because it can touch it, and then a parenthesis on 2, and obviously a parenthesis on positive infinity as it approaches it on the x-axis. So now let's take an example where I'm going to solve a rational inequality algebraically. So the inequality that we're given is 4x plus 5 over x plus 2 is greater than or equal to 3. So let's actually move that 3 over, because I want this to be a 0 over here. So my next step is to actually turn this -3 into a fraction with the same denominator as x plus 2. So I'm going to multiply it by x plus 2 over x plus 2 and work that out. So when I work this out, I notice two things. Number one, my domain is going to be restricted where x cannot equal -2, and there will also be a 0 at x equals 1, because if I plug in a 1, that's going to give me 0 over something, and that is going to be able to equal 0. So I'm going to use that information in order to figure out between what intervals on the x-axis will give me this inequality here, which will satisfy what I'm looking for. So my next step is to actually call into play the number line. And what I do here is I kind of visually map out what I already know. So from the last slide, I know that there's a 0 at x equals 1, so that means if x is 1, y is 0. And then y is undefined at x equals -2. So I know that my graph is going to hit the x-axis at x equals 1 and y equals 0. So what I'm now going to do is I'm going to try to find the y values for 3 other points. So some other negative value that's more negative than -2, wherever x is 0, and then a x value greater than 1. So let's just pick -3 and 2. So I'm going to plug in those x values into my function, see what I get. So with my now paired x and y values, I notice a couple of patterns here. So as x is -3, as it becomes more negative from this undefined value, y becomes positive. And as it moves towards more positive x values, which is x equals 0, it becomes negative. And then we have y equals 0 here, and then as it keeps moving down to x equals 2, it becomes positive again. So when I'm thinking about this, it's going to be positive over the x-axis, right? It's going to hit some kind of undefined value. It's going to then become negative over here. It's going to loop back up to 0, and then it's going to become positive as it keeps going. Now keep in mind that graph probably is not accurate, and that's okay, because I'm only solving this algebraically. So what I now have to notice, or what I now have to figure out, is where it's going to be positive or greater than or equal to 0, because that's what I solved for. So this function is positive coming from -infinity up until it reaches x equals -2, and will become positive again after x equals 1. And it will include that point because of our inequality symbol up here. So the way that I write that looks like this in set builder, where x is going to be an element of all real numbers. It's going to be less than -2. It's not going to include that because it's undefined at -2. And it's going to be x is greater than or equal to 1 because it can include that point at y equals 0. And then I can write it in interval notation with a parentheses at -infinity over here, another parentheses at -2, remember it doesn't include it, and then a bracket around +1 because it does include it, and then obviously just a parentheses around +infinity. And that's going to do it for this video. Thanks for watching.